Okay, what this one? What is the one at the bottom? Is R in frequency domain. So this one tell you, for example, if you have a range of signal, and the signal may have a certain spectrum. So if your input analog signal is with a spectrum like this. So it means at this frequency I have this data, at this frequency I have certain data, at this frequency I have certain data, and the spectrum is like this. And if you have done sampling, this one becomes your sampling data, but if you look at here, this is your sampling data. This is your original data. And your sampling data will be 1 over T. So if you want to recontract back, what you want? You want to multiply with T. So your T R star S will be this one, right? So first of all, this is the reason why you see T R star. Because on the frequency domain, if you have done the sampling, then your sample frequency domain spectrum is infinite summation. You see, this is your original one. A later you will move because your k is from the negative infinite to the positive infinite. So if you have -1, you get this one. K equal to positive 1, you get this one. K equal to positive 2, you get this one. K equal to -2, you get that one. So your sample data is an infinite series of your original RS decompressed by T times, but shift infinite omega S. So this one is your R in the frequency domain, the spectrum. And this one is your sample data. So from the frequency domain analysis, you can see, first of all, your sample data, the magnitude has been compressed by T. And it's not represented by 1. It's represented by infinite possibility to add up together. And this one means if your sampling frequency is not larger enough, then at your sampling frequency, for example, this one, your omega 1, for example, I take omega 1 as my sampling frequency. So at this frequency, what are the possible data you may have? You may get the data from your original R. You may also have the data from your R plus your omega S. Because that one, you have certain portion from this one, you have certain portion from the other one. You may even have some others. If you overlapping, it's too much. And this one is to see from the frequency domain where the aliasing issue comes. It means at any single frequency, you are not corresponding to identical original data. Of course, to most of the students, it's quite difficult to imagine from the frequency domain, unless you are really very keen in math. And you are very keen in math, so you can have a very good imagination on the frequency domain. But all of you should have no problem to understand it through the time domain. So this is the time domain. So what do we mean? If, let me see, your data is this one in red, which is cosine pi over 3. Okay, this one is your original data. And you did the sampling. For example, your sampling time is 1 second. Is 1. Then what the data you sample? You get the blue one, you get the blue one, you get the blue one, you get the blue one. Is everybody okay for this one? This one is okay, right? Just do the sample. But if you got the blue one, can you confirm this blue one means your original signal is from the red color? No. Because if you happen to have another cosine or sine function, which is cosine 7 pi over 3, which is in green. Your green and your red are different signals. Both of them are cosine function, but the relationship is this one compared with this one, your frequency is 2 pi p. Do you notice? This is pi over 3. This is 7 pi over 3. What's the difference? 2 pi. 2 pi. If your time is 1, then your omega is 2 pi. Correct, right? Correct, right? So this one means if my sampling frequency is 1 hertz or 2 pi radian per second. Okay, if my sampling frequency is 2 pi. I obtain the sampling data, I get this one. If you only see the blue one, you want to reconstruct. What do you reconstruct? You can only reconstruct back to cosine pi over 3. Are you going to use this one to reconstruct back to cosine 7 pi over 3? No. So what does it mean? If your sampling frequency is only 2 pi, you cannot reconstruct back to cosine 7 pi over 3. If you want to control back the cosine 7 pi over 3, what do you need? You need more data. You need faster sampling. You need your sampling frequency to be faster. Alright, right? Alright, right? We can also try this exercise through a simple Excel exercise. Actually, I'll show you this file some weeks before. Okay, so if you look at this one, this one, we take the x and we control the step. The step is basically the same as your time period t, yes or no? Right? So I'm going to, this one you can consider as your k, and then your step consider as your t. So in this case, if my t is 1, which means your omega is 2 pi. Omega is 2 pi, so your time is 1. Then you will see no matter you use cosine 7 pi or you cosine 3 pi over 3 or even cosine 11 pi over 3, you get all the data the same. Okay, all the data the same. And if you want to reconstruct back, you can only reconstruct back to pi over 3. But if you want to differentiate, what you have to do, you have to increase your sampling frequency. It means you need to decrease your t. So if I change my t to be smaller, then you can see your different input cosine function or different data. Then there is possibility for you to reconstruct back according to the corresponding frequency. So through this exercise, you have a certain feeling. If you want to reconstruct back your signal at a higher frequency, then your sampling frequency should be faster. Your sampling frequency should be even faster. And this one is something coming to see. The sampling theorem. You can understand this one in two means. One is from the time domain. if your sampling frequency is fixed, omega s, then the highest frequency you can sample back, you can reconstruct back is half. Okay, the sampling theorem you can consider, you can understand in two means. One means is through the time domain, maybe it's easier for you to understand first. So if your sampling frequency is omega s, okay, omega s is your sampling frequency, then the highest frequency you can contract back. The highest frequency you can construct back is half. If this one is equal to your 2 pi over t, this is the sampling frequency, right? Then for your data, if your data frequency omega naught bigger than pi over t, you are not able to reconstruct back. You can only construct back for this one less than half of your sampling frequency. So just now the example, my sampling frequency is 2 pi. So for my cosine function, pi over 3, which is less than 2 pi, I'm able to reconstruct back. But 7, so pi over 3 cosine k e is okay. But cosine 7 pi over 3 kt, you cannot reconstruct back. So this means if your sampling frequency is fixed, you got a limited spectrum, you are able to reconstruct back. This is from the time domain. From the frequency domain, you know where is the omega s? On this figure, you know where is the omega s? This one is 0. This one is omega s. This one is omega s. So what I mean is, from the frequency domain, if your RT, not RT, RS, if your RS is this one, if your RS is this one in your frequency domain, what will be your R star S? What will be your R star S? You will have this one, then plus omega, right? So if your omega S is deep enough, you get this one, you get this one, you get this one, you get this one. Okay? And the magnitude, each one is 1 over t of Rs magnitude. Right? If your omega, this is your omega. This is your omega s. But if your omega s is not large enough, let me see, this one is your omega naught. Your highest frequency, let me see, your highest frequency is omega naught. Your highest frequency is omega naught. If your omega s is not bigger than this one, which is 2 omega naught, then you will have an overlapping. Then you have an overlap. So let me use another paper. This is your RS. Your highest frequency we see is omega naught. And your R star S will be your base one, then you have a plus minus integer of omega s. If your omega s is equal to 2 omega naught, what do you get? This one is omega naught, you have a 2. So you shift this one to here. So you got this one. You see this one is omega naught, then this one is a 2 omega naught, right? And the difference between the two bits is your omega s. So and this is your aging. You don't have any overlapping at all. But if your omega s is less than 2 omega naught, what do you get? So you have overlapping, then you have overlapping. Then at any frequency, your sampling data may come from this one, may come from this one, may come from others. Is it clear? So this one extends the sampling frequency. Why we see your, and if is greater, if your omega s is greater than your 2 omega naught, then there will be no overlapping at all. Okay, there don't have any overlapping. So the sampling frequency you can understand in 2 ways. One is from the frequency domain. And the frequency domain means if you know you have a data signal, the highest frequency is omega naught. In order to fully reconstruct back your signal, your sampling frequency must be at least 2 times of omega naught. This can be seen from here. Alternatively, if you want to see from the time domain, if you have a fixed sampling frequency omega s, then the highest frequency you can reconstruct back is half of omega s. Anyway, it's exactly the same thing. But this one is from the time domain, you are able to understand. And the other one is you need to understand from the frequency domain. So you see this one, if my omega s is 2 times of the omega n, then any moment, any frequency omega 1, I don't have any overlapping. Is it clear? Is it clear about the sampling frequency? Okay, right? So this is sampling theorem. Okay? So this one means one can recover a signal from the sample if the sampling frequency is at least twice of the highest frequency in the signal. So I have introduced 2 ways for you to understand it. Okay? Either from the frequency domain, but that one means if you want to fully recover all the frequency, your sampling frequency must at least 2 times. The other way is, let me say you have a fixed sampler, then the best thing you can get is half of the sampling frequency. The others are not able to make a track. Okay, there are also some online video you are able to learn in details. Okay? And the most difficult part is to understand the sampling frequency, and actually the key important thing is this one. And how to derive in detail the Fourier transform, Laplace transform, inverse Laplace transform. We have this step by step in textbook as well as handwritten notes. Okay? So for the detailed derivation after class, you can refer to the handout written notes, okay, for the detailed derivations. So only important part for the student may not really understand the gem in this one, if I highlight. The rest actually we just apply the Fourier transform, Laplace transform, inverse Laplace transform. Okay, the process itself is a bit tedious, it's a bit complicated, but the conclusion is simple. And this one, the conclusion is this one. If you understand this one, then you understand this one. After you understand this one, then you understand where the aliasing should come from. Then you can extend this. After you are able to extend this, then you are able to understand the sample theory. You must at least have enough gap. Your omega s. You need to understand this one actually is just shift by omega s. Because this one is shift by omega s. N can be 0 MB1, MB2, MB minus 1, minus 2, minus 3, okay? So everything brings out this one. Okay? As long as now you understand this one, you understand this one. Okay? Then you're able to understand the theorem. Maybe we give you a 5-minute break, then we'll continue with the data extrapolation.